going to be a video on just strictly on your KEQ calculations. So when you start your KEQ calculations, it's very important that you're not just looking at the number, but actually reading the question, understand what the question is asking for. So in order to begin, understand that, remember, KEQ or KC, you're looking at the ratio between your products divided by the reactants. A lot of students get this confused because they automatically just find all the numbers in the question and plug this in. But the only difference is that you can't use this automatically in some questions, because this equation is for concentration of products at equilibrium and divided by the concentration of reactants at equilibrium. If you look at this question, it's not at equilibrium. Reactants A and B are mixed in a 1 liter container, each with initial amounts. That means that that's before the reaction actually got started, of 0.8 moles. They react to produce C and D. So then here's the reaction at equilibrium. So then now you're given the equilibrium amounts of C and D, which is 0.6 molar, and you're asked to find KEQ. So in order to tackle this problem, there's a technique called the ice chart, which is basically a table to organize where your concentration is heading, or how much you have starting at the initial amounts and how much you have at the equilibrium amounts. How you organize this is that you're going to put ICE, I for initial, C for the change, and E at equilibrium. And then at the top, you're going to write all your reacting species, which is going to be your A. I'm just going to write my table like this. And then B, this is going to react and form your C and D. You actually don't really need the middle column. So this is your ice chart. So then you're going to use this ice chart and just fill this in all the things that you're given. So you're given A and B with 0.8 moles. We can't use moles, we have to use molarity. So to get the molarity, we're going to go 0.8. What's my volume? I have 1 liter conveniently, so that's just divided by 1. So I start off with 0.8 molar for A and for B. Because this is at the initial, we don't have any of the products, so that's 0 and 0 molarity. So the next thing that we know is at equilibrium, the amounts of C and D are found 0.6. So we know at equilibrium, so we're going to put that under the E, and for C and D, we're going to put 0.6 molar. This is still within the 1 liter container, so 0.6 molar. So this is all that I can put into this table. The next step is we have to see what's the change. So starting at your products, we started from 0 and we actually gained 0.6. That means that it's going to be a plus 6 molar here and a plus 6 molar here. It's a positive because you're in the product, so your reactants actually gain or reacted to gain more products, which is your positive sign. So then we have to calculate, well, if 0.6 actually got created for C and 0.6 got created for D, how is that for B and A? And in order to calculate for here, we need to use stoichiometry. You have to use stoich here. And conveniently enough, you have in this reaction, A plus B plus yields C and D. There's only 1, 1, 1, and 1. That means the ratio is just 1 to 1 to 1 to 1, which is very convenient that you'll get 0.6 and 0.6. And since this is your reactants, you're going to have a negative sign and a negative sign because you're taken away from that. That's the amount of moles that gets used up. So you just do your basic math here, 0.8 subtract 0.6. So at equilibrium, so this is at equilibrium, you get 0.2, and at equilibrium, you get 0.2. So finally, once you have established this row at equilibrium, you can use your KEQ formula, which is going to be your C times the concentration D divided by concentration A times concentration B, and you just substitute all these numbers, 0.6 times 0.6 divided by 0.2 times 0.2, and this will give you an answer of, so let me just punch this in, should be what, 0.36 divided by 0.4, which 0.04, which gives you a KEQ of 9. So once you have established this, it's a good idea not just to stop at the answer, but actually, what does this 9 represent? And since this is greater than 1, that means that you're going to get more products than your reactants. Your forward reaction is actually favored than your reverse reaction. So this is the first type of problem. This is using the ICE table and using stoichiometry just in your change row to see how much change is found in your other sort of reacting species. So that's the first type of question.